So what is the multi-dimensional chain rule from a more, what my grad school professor would have called sophisticated perspective? To find a more sophisticated perspective on the chain rule, we actually need a more sophisticated perspective on what a derivative is. And this is actually a little bit of a sneak preview for where we're going in the next 2 or 3 classes in our course. So far, we've been thinking about derivative as just being a single scalar valued function of a single variable, each one of which is a partial derivative, right? So partial derivatives kind of just isolate one input variable and investigate the changes on the output. But ultimately, if we want to think about the derivative of a function that might have multiple scalar inputs and produce for us multiple scalar outputs, so it could be vector valued function of several variables, then we need something that's more robust than a single number or even sort of a collection of scalar valued functions. We need an object that has a little bit more algebraic heft to it. And so here's what we end up doing. So just to get started, if we think about a vector valued function of several variables, I don't know if you've seen this notation before, but we'll probably see it again at various points in our course. This notation means we have a function called capital F, and that the inputs to capital F are points in n-dimensional space, so n-dimensional vectors, and the outputs from the function F are m-dimensional vectors. So you can think of it as a function which takes n real numbers as input and it spits out m real numbers as output. Or you can think of it as we feed it an n-dimensional vector as an input and it gives us an m-dimensional vector as an output. So that's all that means, right? Examples include, a parametrized curve, which would take a one-dimensional input into a, let's say, 3-dimensional output if my curve is in 3 dimensions. Or a parameterization for a surface would take a 2-dimensional input. So you need an S and a T to produce a 3-dimensional output, a point on a surface in 3 dimensions, right? So there are a lot of different kinds of vector valued functions that we can use in multivariable calculus. And so any time that the types of outputs that one vector valued function spits out are also the types of input that another vector valued function can accept, we can compose 2 vector valued functions together. So if capital G, let's say, takes k-dimensional vectors and makes n-dimensional vectors out of them, and F takes n-dimensional vectors and makes m-dimensional vectors out of them, right? Then I can string those 2 together. I can chain them together and get the composition F of G. Right? All I have to do is take the output of G and stuff it into the input of F. And what I get is a new function which takes k-dimensional vectors in and spits out m-dimensional vectors. Just like, ordinary chain rule or ordinary composition of functions, right? So how then should we understand how to take the derivative of such a composition of functions? Well, before we can deal with the composition part, let's get a more sophisticated perspective on what a derivative can be for the more general case of vector valued functions of several variables. So for one of these functions F that takes an n-dimensional vector as an input and spits out an m-dimensional vector as an output, what should the derivative be? And a good answer to this is that the derivative of a vector valued function of several variables should be thought of as a linear transformation from the tangent space of its domain into a tangent space of its codomain. And that is all a fancy way of saying something that in coordinates we could say, we can think of it as a matrix. So here is one really sort of powerful way to think about what a derivative of a multivariable function actually can be represented as. So we call this the derivative matrix. And I'm going to write it as capital DF. Right? And it's a matrix that has as many rows as the dimension of the vectors that the function outputs, and it has as many columns as the dimension of the vectors that it inputs. Right? So if F takes 2 variables and it spits out 3 outputs, right? If it goes from 2-dimensional space to 3-dimensional space, then its derivative matrix is going to have 3 rows and it's going to have 2 columns at the end of the day. And the entry in the matrix at the ith row, jth column position is just the partial derivative of the ith component of F with respect to the jth input variable. So the derivative of the ith component of F with respect to the jth input. So we can represent the derivative by a matrix. So what in the world might this look like? Let's look at just a couple quick examples. If I just have a plain old scalar valued function, like the kind that we started out studying this semester, f of xy equals xy squared. So that function takes a 2-dimensional vector as an input, xy, and it produces a single scalar as the output, xy squared. And so its derivative matrix has only one row, but it has two columns in it. And those two columns are precisely the partial derivatives, because f only has a single component to it. Then the entries are just going to be the partial derivatives of that single component with respect first to x and then to y. And so we can think of the derivative of this scalar valued function of two variables as this 1 by 2 matrix whose entries are y squared and 2xy. So this is another way that we can think about using the partial derivatives of functions sort of together rather than taking them kind of one at a time. We can sort of package them together into this 1 by 2 matrix. Similarly, because parametrized curves can also be thought of as vector valued functions with a single input, but with a vectorial output in 2 dimensions or 3 dimensions or wherever our curve happens to live, we can find their derivative matrix as well. But that derivative matrix is going to have 3 rows and 1 column, because it's taking one scalar input and giving us 3 scalar outputs. And so there's 3 derivatives in this example. And I've written them as though they're partial derivatives, but I probably shouldn't have. These should probably be written as ordinary derivatives. And what we end up getting, this derivative matrix, actually looks a whole lot like the velocity vector to the parametrized curve, right? It has all the same components, just instead of thinking of it as a vector written in coordinates, it looks like a column matrix. Those of you taking linear algebra with me this semester are going to get real sick, in a good way hopefully, of representing points in a vector space as column vectors, right? That is typically how we work with vectors in linear algebra. And so the derivative matrix is just the velocity vector, but as a matrix that's written in a column. How about for a parametrized surface? For a parameterized surface, we're taking 2 parameters as input and spitting out 3 scalar outputs. And so its derivative matrix is going to have 3 rows and 2 columns. So in this example, the first column would be the derivatives of my parameterization with respect to the first parameter. So derivative of s cosine t, s sine t, s plus t with respect to s. And then the second column are the derivatives of the components with respect to the second variable, which is t. So minus s sine t, s cosine t, 1. And so this derivative would then be a 3-row, 2-column matrix. So this is, I think, what my professor in grad school was looking for as a sophisticated understanding of the derivative, right? We could also sort of call back to when we talked about tangent planes a little while ago, because again, when we're taking and finding an equation for a tangent plane, what we're really doing is we're taking the partial derivatives f sub x and f sub y, multiplying them by x minus x naught, y minus y naught, and adding the results together. Well, we can represent that as the multiplication of a 1 by 2 matrix, which is exactly the derivative matrix that we talked about before for a scalar valued function, right? It was just the x and y partial derivatives written as a row matrix. But then multiplied by a column matrix, which is the differences, x minus x naught and y minus y naught. So if this is my derivative matrix, then this thing in the parentheses over here is the difference between an arbitrary xy and the x naught, y naught that we found our tangent plane at, where we linearized our function, however you want to say it. And so it looks an awful lot like, if we re-express these as kind of vectors, instead of as individual scalars and components, that z is equal to f of the vector x naught that we know, plus the derivative matrix evaluated at x naught, multiplied by x minus x naught. And so in this format, it looks exactly like the equation for a tangent line looked in single variable calculus, right? In single variable calculus, a tangent line to a function is y equals f of x naught plus the derivative at x naught times x minus x naught. Same thing, just with the x naughts and the x's being vectors now, and the derivative being represented by the derivative matrix. So the derivative matrix gives us a lot more powerful sort of tools to use, because matrices have a very rich algebraic structure that you learn a lot more about in linear algebra. And so in this perspective, what the multivariable chain rule ends up looking like is it ends up looking exactly like the original single variable chain rule. It says that the derivative matrix for the composite function f composed with g is nothing more than the derivative matrix of f multiplied by the derivative matrix of g. But the derivative matrix of f has to be evaluated at the output of the g function. So this is just the higher dimensional analog of, in the single variable case, the derivative of f evaluated at g multiplied by the derivative of g. It's just that now, instead of multiplication of real numbers, this is multiplication of matrices. So if I wanted to put this multivariable version of the chain rule into practice, let's try to use it to revisit this problem from the activity that we just wrapped up, which gave us this sort of complex composition of functions where we start with a single variable t, and then from that we produce a u and a v, and from the u and a v we produce w, x, and y, and then from w, x, and y we produce a z. Let's see how the multivariable chain rule could actually make the work that you did with this network diagram a little bit quicker. So to do this, let's just write down what are the functions that are being composed in this example. So we start with a t, and then from that t we produce a u and a v. And so I'm going to think of that as a vector valued function, right? U and v. And so let's call this first function something. Let's call it capital H. Right. So there's a vector valued function that takes the t and it turns it into a u and a v. Then there's another vector valued function that turns those u's and v's into w's, x's, and y's. And so that u and v becomes a w, x, and y through the application of another function, which we'll give another name. Let's call it g. And then finally, the last step is that w, x, and y get transformed into a z by the application of a single final scalar valued function. And let's call that scalar valued function, let's call it little f, using a lowercase, just because that's what we typically use for scalar valued functions. So let's think about how the multivariable chain rule, the matrix version, should help us to find the derivative of z with respect to t. Right. So according to the multivariable chain rule, let's put it back on the screen here for a second. Multivariable chain rule tells me that the derivative of a composition, the derivative matrix of a composition, is the matrix product of the derivative matrices of the original functions. And so if it works for a composition of two functions, it also works for a composition of three functions. So let's sort of write that off to the side here, that the derivative of my composition, right? My composition is really f composed with g, composed with h, as a function of t. So what this derivative is, according to our multivariable chain rule, is the derivative matrix of f evaluated at the appropriate inputs. I'm going to suppress that in the notation just to make it easier to look at, multiplied by the derivative matrix for g, again evaluated at the appropriate inputs, multiplied by the derivative matrix for h. So let's find coordinate expressions for each of those derivative matrices, and then we'll do the matrix multiplication that makes our final answer pop out. So starting with my scalar valued function over here on the end, right? For a scalar valued function, remember the example we looked at a minute ago here for derivative matrix. For a scalar valued function, that derivative matrix ends up being just a row vector, right? Where the entries in my row vector are just the partial derivatives of that scalar valued function. And so the derivative matrix here on the end is going to be a row matrix, which is the derivative of z with respect to w, derivative of z with respect to x, and the derivative of z with respect to y. So there's the derivative matrix for the last function f. Let's do the derivative matrix for our first one, derivative of capital H, because this is an example of a vector valued function from one dimension into two dimensions. So this is like a parametrized curve into two space. And we did an example a second ago that looked like that, right? The derivative matrix for a vector valued function of a single variable ends up just being a column vector, right? It has as many rows as we have outputs, but it has only one column because there's only one input variable. And so that means that this derivative matrix is just a column vector, and the entries of that column vector are the derivatives of my two components, so du dt and dv dt. So I have a 2 by 1 matrix for dH. I have a 1 by 3 matrix for dF. And then I have this g function in the middle. This is the most interesting function of the bunch, I think. So if I want to find this derivative, so now this is going to be a proper matrix, right? It takes two variables and it produces for me three scalar outputs. So this looks an awful lot like the derivative matrix of a surface parameterization, like the one we looked at here a minute ago, right? And so its derivative matrix is going to have 3 rows because it's outputting 3 quantities, and it's going to have 2 columns because it's inputting 2 scalar inputs. And so the entries in this matrix are going to be the derivatives. All right, so going, all right, so it's the derivatives of w, x, and y with respect to u, and then with respect to v. V, dx, dv, and dy, dv. Ugh, all right. And that matrix then has 3 rows and 2 columns. So before we do any matrix multiplication, we should always make sure that the dimensions of the matrices that we're multiplying are actually compatible. This is going to be the case only if these 3 functions are the kinds of functions that we can compose together, only if the outputs of one of them actually fit into the inputs of the other, right? So, for example, our h function is spitting out 2 outputs, and the g function is taking 2 inputs, and so we can match those 2 together. And their derivative matrices, so dH was 2 by 1, dg was 3 by 2, and we notice that those 2 matrices can be multiplied together because dg has as many columns as dH has rows. And when you multiply matrices, you need for those 2 things to be equal. Right? So that works out. All right, so those are equal. So that's good news. That means we can actually do that multiplication. And then the same thing is also true for dF, right? G is spitting out 3 scalars. F is taking in 3 scalars as input. And so because that composition is compatible, we should also see that the matrices for their derivatives can be multiplied too. dF is 1 by 3. dg is 3 by 2. And so because the number of rows in dF, the number of columns in dF matches the number of rows in dg, we can multiply those matrices together. So we can do this matrix product. All the dimensions match up to what we need them to be. And when I do the matrix product, the final answer is going to be a 1 by 1 matrix. It's going to be a single number, which is what we expect after all, because the composition F composed with G composed with H takes a single input and it produces a single output. So its derivative matrix is just going to be a 1 by 1 matrix whose entry is going to be the derivative of Z with respect to T. All right, so enough avoiding the hardest part of this whole process is actually doing the matrix multiplication. So make myself a little bit of room here. So to get the derivative of F, I'll write that as dz dw, dz dx, dz dt, dz dy rather. So that's df. And then in the middle I have dg. So that's going to be this big thing, dw du, dx du, dy du, dw dx, dv rather, dx dv, and dy dv. And then my third matrix that I'm multiplying together is the dF matrix, which is ordinary derivatives, du dt and dv dt. And now is when we remember how matrix multiplication works. So matrix multiplication works by, for reasons that my linear algebra students will see later on in our course, when I multiply a pair of matrices, let's say I want to multiply the second pair here, what I'm really doing is I'm taking a dot product of each row of the former matrix with each column of the latter matrix. So if I want to find the first entry in this product, I'm going to multiply dw du times du dt, and I'm going to add it to dw dv times dv dt. So that's going to be the first entry here, dw du dt, plus dw dv times dv dt. So we go across the row of the first matrix, down the column of the second. And then we keep going. Right? dx du times du dt plus dx dv times dv dt. And the third entry, dy du dt plus dy dv times dv dt. So now we've done the product of the second and third matrices, but we still have one more matrix product to do because we have this d little f. Or no, sorry, d little f sitting out here in the front. So dz dw, dz dx, and dz dy. And so to do this multiplication, it's just a row vector with 3 entries times a column vector with 3 entries. And so there's only one row in the first matrix, there's only one column in the second matrix. So I only have one row to multiply across and one column to multiply down. And so when I do that, what I get is dz dw multiplied by this whole first entry. So I'm going to try to write this out as well as I can here. So dz dw times, and then in parentheses here, I'm going to put dw du du dt, du dt plus dw dv dv dt, added to the second component, multiplied by the second component, dz dx, multiplied by that second component, which is dx du du dt plus dx dv dv dt. And then finally, the third component multiplied by the third component. So dz dy multiplied by dy du du dt plus dy dv dv dt. Whew. And that ends up being a 1-by-1 matrix, in other words, a scalar function. And sure enough, when we do this multiplication out, we get the same 6 terms that we got when we used the network diagram sort of approach to this. So the matrix multiplication viewpoint of the chain rule, where the derivatives of our functions really are linear transformations, which in coordinates are represented by matrices, that matrix multiplication just reifies this same structure of using a tree. But the benefit, again, of thinking of the derivatives in this way is that it gives us sort of a different perspective that is easier to kind of generalize into other areas of mathematics for what a derivative of a function of several variables actually is, what it represents. So this is both kind of a nice connection between linear algebra and multivariable calculus, but also the kind of connection that will enable you later on, should you choose to do so, to do things like study the differential geometry of curves and surfaces, to talk about the analysis of multivariable vector-valued functions in a multivariable analysis course. That once you have this, for me, this was one of those paradigm shift kind of moments that, oh, wait, the derivative is a linear transformation. It's not just a function. It takes vectors to vectors, and we can represent it by a matrix. That was a big sort of epiphany for me in my own mathematical education. And so it's one of those things that I don't get the opportunity often enough to share with students. So I appreciate your indulgence.